like them. They're still on mic. Okay, you got it out? All right, we really appreciate everybody coming out. The purpose of this meeting is to show you a new extraordinary source of power, and to put it in perspective, it's a power source greater than anything controllable that I'm aware of on the planet. I know it's a big statement. So you might ask, well, what would that look like? Extraordinary, more powerful, say a million times more powerful than internal combustion engine. What would that look like? Well, it would be pretty loud, and it would be explosive, because power is energy over time. Energy is heat, light, and other projectile kinetic energy. So what we're going to show you is a demonstration, and we're going to do a sort of a scaled down version, and we're going to show you two different forms of fuels that produce plasma. Plasma is the state of matter, such as in the fluorescent lights in this room. It's ions, which are electrically conducting. It's a gaseous state, and it's remarkably, it's created from metal. So you're looking at metal that's been basically transformed into an ionized conducting gas because of the enormous amount of power that's released in this reaction. The reaction runs for a very, very short period of time. If it ran continuously, we wouldn't be able to stay in this room. I'll give you the specifications of it after we show some of the demonstrations. But this is first just to show that there's power released. It's released so fast, it's your eye can't capture it. You can just see some phenomena related to it, light and sound. It doesn't really produce gas other than vaporized metal, so it's not like explosive that produces a lot of gas and has an expanding gas shock front due to that. There will be a shock front. That's why we ask people wear ear protection. They call that a shock wave. It's a high pressure wave, moves supersonic, faster than sound speed, and it could hurt your ears. Even though it's not making a lot of gas. It made a lot of gas, and it would be very, very, very loud. We're going to run this in a power system that's in vacuum, so this will be plasma expanding in the vacuum and then being converted directly into electricity. So what we're going to do is just show the phenomenon. We've done calculations based on phase transformations. It's involved in how much energy it takes to melt metals, to vaporize metals, and to put them into an ionized state. So the amount of power we can calculate from that. But since you're not scientists, this is just a visual demonstration of the form of matter that we would create and then transform into electricity in our devices. So Johnny's first is Johnny Mikowski. I guess I should introduce myself. I'm Randall Mills, the CEO. And we have Dr. Ying Liu and Dr. Julian Yee. Ying is going to demonstrate the characteristic signature of why this energy is released. It forms a more stable state of hydrogen. And all forms of matter, elements, atoms, etc., have a characteristic light signature that is characteristic of and identifies them. The hydrino is a more stable form of hydrogen. We form a hydrogen atom with the electron titer bound to the nucleus, which is a proton positively charged, electrons negatively charged. When their separation distance is diminished, you get energy release. And there is a mathematical curve fitting theory called quantum mechanics. It's postulated. You can't really define exactly what it means in terms of mechanics, because it was never really meant to be a mechanical theory. It's purely mathematical. And there's really no solution of the electron in that formula. It's just a sort of an This is something was predicted from classical laws that are the foundation of our modern society. There's actually an exact solution of what an electron really is. It has charge, it has mass, and you can treat it just like you treat any other engineering problem. And the equations are absolutely exact and perfect, have fundamental constants only in them. I'll talk a little bit about that. This isn't a theory lecture. But the point of it is, for that electron going down to these new states, which the current theory or the old quantum theory, mathematical theory would say that's not possible because they didn't know they existed back then, and that theory was just invented to match what was known back then. It's not predictive of anything, it just matches things. It's a curve fit. So if you don't have the numbers of curve fit, you don't know where those, you can't make math the curve fit, and you don't know what the curve fit is. So this is actually predicted, and what it shows is that theory is wrong, absolutely wrong. The way theory works is theories can never be proven, but theories can definitely be disproven by an experiment. This experiment shows that hydrogen can have more stable states by emitting an extraordinarily high energy plate that has a pattern length over a very, very large range of wavelengths and energies. Typically, atoms have an ion, which are ionized atoms, have discrete spectral lines. These are very, very narrow frequencies of light that identify that particular composition matter. In this case, the light is like white light. It's a combination of light. If you take a prism and then bend it light through a prism, you'll see it has different colors in it. So it's a combination of different frequencies and wavelengths of light. In the transition of this hydrogen atom to this new state, you get a very, very broad range of energies coming out simultaneously due to the nature of the transition. Then once it gets to that lower level, it's absolutely stable. It cannot emit light, it can't absorb light, it's dark. And what I'll do is go into the other characteristic that we think that it is the identity of the dark matter of the universe. That might not mean much to many people, but if you look out there in your astrophysics, you'll see almost the entire mass of the universe is made of something that has not yet been identified. That matter can be observed by its gravitational effect, but it does not absorb or emit light. And you can also see the same type of light we're emitting in our experiment that Ying is going to record today and making this new state of hydrogen. You can see that in the storms, in the sun, and in the interstellar gas, the gas that is in between galaxies, or between stars within galaxies. So, let me get on with the demonstration. Then finally, the last part of the demonstration schedule is that Dr. Ying Wu will measure the heat release from this reaction. So you'll see it in terms of visual evidence. It's obvious from visual inspection. There's an enormous amount of power being released. We'll actually quantify the thermal equivalent in a calorimeter. That's a device that is a commercial instrument that measures energy release on reactions that are very, very fast and release a lot of energy in a very, very small amount of time. The heat is absorbed in water, and then we measure the temperature rise of water, and there's a very characteristic way of measuring heat. This is the most accurate and most reliable way there is of measuring energy release in the form of thermal energy. So with that said, Johnny here is going to demonstrate first what we have as the source to ignite this new type of fuel and release this incredible amount of power. We have a commercial, all things a commercial spot welder, and what a spot welder is a unique power supply. If you look at commercial sources of high current, this is the most reliable and high current source that you can find readily available. And the kinds of current that we're trying to apply to our solid fuel is very high. It's about 1,000 times the current that would trip the circuit breaker in your house. So we're going somewhere around 15,000 to 20,000 amps. The interesting thing about this is this reaction to form this more stable hydrogen called hydrino has a limiting step. And I'll show you a graph of what that limiting step is. But fundamentally, when the hydrogen goes to a new state, it transfers energy to something that accepts it. And in the process, it builds up charge. If you do not remove that charge, the reaction becomes self-limiting. Applying a very high current to this fuel creates the hydrogen and the acceptor of the energy to make this new hydrogen called hydrino. It means that for small hydrogen. It has a smaller radius than ordinary hydrogen. Again, it is probably the most ubiquitous substance in the universe. It's completely inert, completely stable. It's lighter than air. You can't keep it in the atmosphere. There are many ways of identifying it. Once you know what it is, you have the correct theory of predicting what its spectral signatures are, not only in the instrument that Dr. Lou is going to show you, but also there's analytical text in terms of the vibration and rotation of corresponding molecular forms and other spectroscopic ways of analyzing it and identifying it. So, we want to show that this spot water has a very definable waveform, very definable current. That current, when flowed through the fuel, eliminates that self-limiting charge buildup, and we can get the hydrino transition to go what you would call catastrophic rate. A rate so fast that it basically detonates. And the fuel is comprised of essentially all water. The active ingredient in the fuel is a remarkably H2O, like in this bottle right here. Literally what we're doing is taking a chemical and we're putting water in it. No water, this effect is not observed. So we have to make the water conductive to get that amount of current through it. The voltage here is very low. It's like the voltage of 2 camera batteries. So very low voltage, and to get any kind of current through, especially that incredibly high amount of current, the fuel has to be extraordinarily conductive. So what we have is we have metal that we put into the system. It absorbs water. We pass the current through. It eliminates the rate-limiting, self-limiting step of the reaction to form this new, more stable form of hydrogen, and it literally explodes. We've had experts look at this in terms of amount of volume of material, and it is remarkable. You think of all the high energy, what they call high explosives, like RDX, PETN, like pentaritrol, tetranitrate, all these different things. This is actually more energetic on a volumetric basis than that. It's enormous amount of energy. We just are getting into making the kinetics more and more rapid and releasing more and more power as we progress with our program. But we're just going to show you something that is not too extreme today. So first John is going to demonstrate that the spot welder is nothing but extraordinary low voltage. You can see you can touch those rods. They're completely safe because it's extremely low voltage, but it produces a high current. So I'll show you, we'll put the current through a wire. There's nothing magical about it. Do you want to do that? So I have the gold wire loaded on there, and I'm just going to pass the current through it. Gold was selected because gold is very conductive, and that's the standard waveform. It's the output of the spot welder. There's a white trace, which is the current. It can go up to as high as 20,000 amps, and then there's the voltage, which is important. The voltage is extremely low. You can see it peaks out around 8 volts, and there's something called a root mean squared. It's a number they use, and it's kind of like the average over a cycle, and it's about 6 volts. So very low voltage. We've got 10 you can see here, let me point this out. So where this is, there's 2 electrodes here, and then you see those big bars, those big copper bars, is the conductor for the electricity. He's going to close that pneumatically, and then it's going to, the current will, those electrodes are big rods, will come in contact with the wire, and then electricity will flow through the wire, and it's just your standard kind of spot welding action. So right there is where the focus. 3, 2, 1. That's it. So it's just a standard old spot weld. Nothing major there. Yeah, you can see the waveform up there in terms of the voltage and the current on how the thing operates. So next, Johnny's going to put in, again, sort of one of the mild fuels. This is nothing more than H2O, like this, nothing different, and copper metal. And it's put into a what they call a differential scanning calorimetric pan. We just have a pan to hold it, and that helps with the conductivity, getting the high current through it. Copper is very conductive, so we use a powdered metal, and the water gets displaced and mixed in with the metal, and the metal is going to conduct electricity and allow this new reaction to occur. So we call this one the Jumpin' Johnny. Three, 2, 1. All right, let's set off another one. So that was a lot of power. We're going to pass around a, do you have a German doing pass around? So this is a Jumpin' Johnny. Basically what it is almost all water. There's 2 layers of metal. There's a cup and a cap, and the cap's pushed in almost to the bottom of the cup. And in between there is a very thin microscopic layer of copper metal and water. So it's almost essentially nothing but a little tiny bit of water. So this is what we're getting. One thing I should point out, we can measure the energy input with this by taking the voltage and current and then looking at the total energy input. So when we do the calorimetric measurement, that's really important. We have fuels that the amount of energy coming out is up to 100 times more than it takes to detonate it. And that can be made vanishingly small. So there's a huge energy gain. So we're putting energy in to ignite it, but we get a lot of energy out. And the power is higher than anything controllable so far ever conceived or discovered by man. Three, 2, 1. That's a jumping jump. Okay, so next we're going to do another type of fuel. That one we had in a vessel. The commercial embodiment of harnessing this new source of power would entail taking a solid fuel and putting it into a system where we could detonate those, ignite those very, very frequently. In fact, we would detonate faster and faster to the point that you would usually distinguish anything other than continuous. We have to make a continuous power. So to do that, we would use a solid fuel. The solid fuel is, in this case, is a mixture of a material that absorbs water, and a material that makes the solid conductive. So the particular compositions of matter that we have in the next fuel, which we call a Q Christie, is that we have silver metal, and it's predominantly that, and we have, in addition to that, magnesium chloride, which is a hygroscopic material. It forms a pentahydrate. That means it has 5 water molecules that it absorbs. It can absorb this right out of the atmosphere. And that combination gives you a very, very huge amount of power in terms of the fuel. So that's basically it. The conductor and the material that absorbs water. In both cases, I want to point out, I'll pass one of these around. You got to keep this here and pass it around. Okay, so this is this little green thing here. I'll pass that around. That was almost all silver, and the other active ingredient, you put it in the spot welder. Silver obviously doesn't do anything in a welder. You put metal in, nothing happens other than to weld it. Cleansing it partially melts it, so you can fuse 2 layers together. But what the Q Christie does is something quite differently when we put the water in there. So we would put that in our solid fuel chamber in a power generator, and I'll show you how we can flow that particular kind of fuel into that generator and make power continuously. So Johnny's going to show that now. The explosion was suppressed because the pellet poured into the metal and welded together. It takes a lot of energy to do that. So I'm going to shoot off another one. Very small. Three, two, one. Alright, well, anyhow. You're spared the big blast because the rods are melting and fusing together, which is a good thing. It shows there's an enormous amount of thermal power being released in that tiny little pellet. It actually takes a lot of energy to melt those rods. The commercial welder, the electrodes don't weld together, and that's the whole idea of a commercial weld. But it's welding. Q Christie is welding our electrodes together. So, what do you think? You think it's going to weld again, or you can do it? Sometimes it excoriates and blasts out the side of the electrode. You get a nice some fireworks, but it looks like we were welding. Okay. So, all right. So we're going to have Dr. Luke start his equipment. He has to pump down his chamber. And Dr. B is going to start up his calorimetric system. And again, it's a commercial calorimeter. It's made by a company called PAR, which is a very, very well-known brand of instrument for making calorimeters. Calorimeter has in it a means of sensing the temperature. It has something that absorbs the heat. In this case, it's water. There's something about water called a heat capacity. It's the amount of energy it takes to raise the water a certain defined increment in temperature. And from those known parameters and properties of water, you can put thermal energy into it, measure the temperature rise, and it'll tell you exactly how much energy to extremely high precision went into the system to cause that temperature rise. This is model number 1341. Again, it's a standard commercial instrument, all new equipment. So he has another spot welder that will pass current through the rods. You can see there's two connectors, and there's electrodes going into this water bath calorimeter. And in there is one of the copper systems. It's copper metal, copper oxide to help absorb the water and make it more dispersed, because we lose a lot of current on those smaller diameter rods due to the fact that inside that water chamber, the chamber that has the water, we have submersed a cell that's filled with helium and has the electrodes and contains the sample. And I have to say that the detonations you saw have no theoretical energy possible. What that means is what you observed is not possible by any known conventional reaction. So that energy is being released by something entirely new. And it's entirely dependent on water as being present and the high current being passed through it. So now we're going to measure the thermal energy from one of these fuels. We put it in helium, so it's an inert atmosphere, and the helium helps transfer the heat from the ignited fuel to the water, and it helps that coupling allows that to progress more favorably, so we get capture of that thermal energy released in that fuel in that water. So we get a very accurate reading. So we can't detonate it as well in these systems, but we still get a very substantial amount of energy, because theoretically there would be no energy possible. So Julian's going to show that now. Ying's pumping his system down. I'll come back to that. He's going to take some spectrum. I'll talk about that when Julian goes ahead and detonates his system. It'll take a while to integrate the energy, so we'll come back to him. I'll give a presentation about how we can apply these two energies. Okay, it's detonated. So now his temperature will be rising. I'm going to switch to the screen. Okay, he showed you the waveform, so we can integrate the voltage and current, and now you can see the temperature starting to rise up there on the right-hand corner of the screen. So that water is going up in temperature, and then we can measure that temperature rise when all the heat has been transferred to the water, and get an accurate measurement of the heat released in that detonation that he did inside a very, very strong cell that's submersed in that water bed. It's good and strong because we don't want to destroy our calorimeter because those are expensive. Okay, so now Dr. News is going to pump his system down, and then he'll get ready to detonate. So you let me know when you're ready to detonate. Oh, you are ready? Okay. He's going to detonate his system. What he has is a extreme ultraviolet spectrometer. Why don't you go ahead and detonate, and I'll explain why you're doing it. So he has, again, another commercial spot welder. He has two electrodes that are going into a solid fuel. It's in a vacuum chamber. You don't have to use your earplugs now because that's in a vacuum chamber. You can't make sound in vacuum. So, and it's in a very, very solid, very thick walled chamber. So that little click, he just now exploded inside the chamber. The pressures in these detonations get very, very high. They can get well over 10,000 atmospheres, or 10,000 times the pressure in this room. But we have a big expansion chamber there. You can see that chamber where that blast expands and allows the light to come out. This is a different kind of light than the light in this room that your eyes are responsive to. won't even go through a centimeter of air. It's what they call extreme ultraviolet or assault X-ray. Now usually you think of high energy light as being very penetrating. Well, that's X-rays and nuclear kind of stuff, which is very bad and dangerous. What we're doing is something that's very, very safe. This light can't even go through air, even a minuscule amount. So we have to have this system under vacuum. That light then travels to this unit on the end. That's called a spectrometer. And in there is something called a grating. And a grating is something that takes light and breaks it into its characteristic component frequencies. And each frequency corresponds to a wavelength, or if you want to think of it in terms of visible, a color, and a energy. And that light from that instrument will show that these light is much higher energy than any known chemical reaction by about a factor of 100 times. And there's no alternative explanation because there's no other source of energy. There's no high electric field that can create that extraordinarily high energy. So he's going to report that and show that. We've had world-renowned experts in to look at this. This is absolutely the smoking gun, unchallengeable signature and proof that we're making a new state of matter. This absolutely disproves the current theory of quantum mechanics that you can't go below the ground state. This is a very, very profound experiment. It directly disproves that. Again, I said you can't prove a theory, but you can disprove a theory by an experiment. This disproves that theory and confirms that we're making a new state of hydrogen as the source of that blast, that high power that we saw earlier. And then in Julian's experiment, Dr. He, you'll see also it makes thermal energy that can't be explained by conventional chemistry or any conventional prior understanding of water and hydrogen. So I'm going to show you next the how we can make this into a power source. So I want to just show get the temperature going up one more time, and I'll come back to my presentation. Okay, we're just looking and you can see the temperature is rising in that calorimeter. So the thermal energy is being transferred to that water as I will be speaking here, and then we'll come back and we'll get the reading of the energy that was released in that very, very minusculely small amount of fuel. So I want to talk a little bit about how minusculely small that is. So typically what we get in these detonations that we can measure by a number of different methods is on the order of 1,000 joules. Now, you know, maybe this particular pellet we're going to set off in here is probably going to be around 300 to 500 joules. That won't detonate completely. If we detonate completely, we typically get about 1,000 joules of energy from that amount of material you saw in the Jumpin' Johnny and the Q crystals. That is a lot of energy for very, very small volume, because I'll tell you what it translates into. The volume in there is about 100,000th of a liter. So, and you can see from the time scale of the trace that we were taking earlier when we detonated the pellets, the solid fuel materials, the time scale is about 1,000th of a second. And actually, munitions experts, that is people that work with explosives, said our time scale is much, much shorter than that. But we're just looking at the mechanical time scale when that system is disrupted by the pressure wave created by that ignition. If you take 1,000 joules of energy that's released in 1,000th of a second, which is extremely conservative, probably in the microsecond time scale, you get 1 million watts. So that blast you saw is on the order of millions of watts. The volume of that fuel is 1/100,000th of a liter. So if you have 1,000,000 watts in 100,000th of a liter, you have 0.1 terawatts per liter. what is a 0.1 terawatt? The entire electrical generating capacity of the United States is about 0.6 terawatts. So 0.1 terawatts is an enormous amount of power. That is more power per unit volume than is controllable by a factor of 1,000,000 of anything on this planet. This is absolutely controllable. We can ignite those pellets as fast as it can feed into that power supply. And we are building systems that will do it essentially on a continuous basis. That will fly to an electric converter and make electricity. So this is a very, very big deal. It changes the entire definition of power. People used to think, oh, I want to make my car faster than my neighbor's car. Or I want to win this race in a Formula 100 race. This would be 1,000,000 times more powerful than a Formula 1 racing engine on a volumetric basis. That is a very, very big increment in terms of improvement on the state of the art. So, I give you another metric. If you were going to think about it in terms of power, if you drive by 3 Mile Island, or if you look at the Fukushima power plant with the 4 nuclear power reactors, 3 of which exploded, and spread radiation over many miles, and you can't inhabit that Earth for a long time. If you look at those 4 reactors, you could replace them with 1 liter of this reaction. And this is absolutely safe. No toxic chemicals, no radiation. It makes a more stable form of hydrogen, most ubiquitous form of matter in the universe, and it is absolutely unreactive. It is the most stable chemical you'll ever find in the universe. So, getting here, there's of course, there's a lot of energy consumed in the world, and there's really need for more energy. So, one of the things we're looking at is making a 10 million watt reactor. That would power 10,000 homes. And it would do it very, very cheaply. We anticipate the cost of electricity to actually be a very, very small fraction of a penny per kilowatt hour. There's no fuel cost. You use water that you can acquire freely from the humidity in the air. The systems projected, I can go through the systems, you can do the math yourself. They should be extremely cheap. They should be about 1% the cost of conventional systems. Even if we're 10%, it's going to be extremely cheap. And I'll actually give you, ballpark numbers as I go through the parts, so you can add it up. It's not going to cost very much for this equipment. So, basic idea is that our modern society is based on F equals ma, electrodynamic equations, or you can actually calculate if you want to make a transmission line, or you want to transmit radio signals or whatever. There are certain equations you can actually predict exactly how things will work. Those are engineering equations based on classical physical laws. Classical physical laws were abandoned because no one could really solve what the structure of the electron was. Everyone just said, well, let's just model the atomic system. We don't, as a black box, we'll just assign a wave equation, which is like a probability type of model, and it'll just spit out numbers. We won't really have to understand what the position of the electron is or its energy. We'll just say it's everything at once simultaneously. We take like an average, and we can adjust the parameters to make it work how we want it to work. And we can continue to do that in more and more complicated systems by adding more and more adjustable parameters and more math. But there's no mechanics involved. There's no fundamental understanding of how it works. Therefore, it's not very predictive, which is kind of a limitation. What we're looking at in our technology is applying those very exact laws to the atom. You can, in fact, solve what an electron is. Everyone would say you can't do that. Well, you can't do that with the current theory, but you can do it with the known laws of the universe. And how do you know you have the right solution? Because it gets everything from particle masses to predicting the acceleration and expansion of the cosmos before it was observed absolutely correctly. And predicts things that people have not observed, including many of the new experiments that the current theory is missed and failed miserably. It's got every single test perfect. So it's extraordinarily accurate and predictive. That's how you know you have a good theory. And it's actually the same theory that they teach at every university in the world that almost all people learn when they're going through physics and chemistry is the basic laws of nature that absolutely work at the atomic scale. Everyone says those laws don't work at the atomic scale. Well, guess what? They're wrong. They do work at the atomic scale. There's not a macro scale and an atomic scale. There's just physics that works on all scales. No one solved it correctly or did the hard work, and that's why they're blundering around with formulas that are purely perfect and they don't work. So this absolutely is accurate and works. And it predicts what you're seeing today, and the current theory doesn't, and that proves that it is wrong. So this is a computer-generated model of the electron. You can actually model the current the same way you model of the electron, the same way you model current in an antenna or some other physical problem. It's the same types of equations, and it works very elegantly just as it does on the engineering scale. And then you can solve things that you couldn't even fathom solving with conventional theory. You can actually solve and then build up molecules on a part-by-part basis. You know how to build a building? You don't say a building's a quantum wave function. You say a building is bricks and steel and parts. You solve the parts, and they go together, and you get something really complicated. But it's made up of little pieces that are much more simple. So you can solve the individual units that make up molecules. Then you can quickly add those all up and get molecules of boundless complexity and boundless extent by adding those parts together. And guess what? When you add the parts together, the current theory says you can't do that. It works absolutely perfect. Again, proving that the current theory is not correct. How do we know that? Well, you can take 415 molecules and you can add the parts together. And here's the calculated and experimental here. And you can see it's a perfect line. To the limit you can measure these experimentally. This is the current theory. It looks like a shotgun just straight across the screen here. And you'll see, oh, they'll point to maybe this one point. You can just work on the line and say, oh, the theory works perfectly. But how about all the cases where it doesn't work perfectly? That's what really matters. It's got to work perfectly every time where you don't have the right theory. So the other thing that condemns the current theory and further disproves it is you can actually now image what molecules look like. So the current theory says you can't really show a picture of an electron or a molecule. The electron's everywhere at once simultaneously. It has no physical form. Cannot be defined. Well, guess what? You can absolutely image the electrons in molecules now. This is a molecule called pentacene, and there's a technique called atomic force spectroscopy that's gotten more and more accurate. And this is the solution using physical laws. You can see here there's an atom here, and there's different bonds here, and you can see it superimposed very, very well. And all the energies and parameters you can calculate with these physical laws match the limits you can measure. So this is absolutely, like you saw with the experimental evidence from the detonations, seeing is believing. A picture speaks 1,000 words. You can actually see molecules, and the solution has to match that picture, and our solutions do. And the quantum theory would say you can't make detonations from water. Water is the most known substance, and nothing, we don't know anything out there that you can possibly fathom that doesn't match our theory. Well, guess what? Their theory would say it wouldn't detonate, and you just saw it detonate. And we also have instrumentation on the end that it's even more compelling. We can take a material, not even a fuel, but water itself, and detonate it initially with a high current and form something called arc plasma. And once that forms, you get extraordinary high current through water itself, and it will make power. We have that on the end, and then finally on the table on the far end, we have something called a differential scanning calorimeter, where we can make fuels not pass the high currents and power densities, typical of what you get, say, in gas turbine, kind of in the conventional realm. Ours being unconventional, but that's a commercial instrument, and we've shown that to many validators, validated on off-site facilities and many facilities, and some of those reports are on our webpage. So that commercial instrumentation is on the table there at the end. So the way the black light process works is you have a hydrogen atom that has a stable state and cannot emit radiation. But if you put that in proximity to something that can accept energy from the hydrogen atom in a discrete amount, that energy will flow to that acceptor, and the electrons will have to be ionized as a consequence of accepting that energy. In our case, what I was saying before, these particular electrons, or this step of the reaction, are limiting. So the reaction will propagate until that charge builds up. It does not take much charge to build up until the reaction becomes limiting. So we run a very, very high current through it, and that allows that reaction to propagate at very, very high kinetics. We then form an intermediate that, you can see the dotted dashed line. The hydrogen atom has its initial radius, but it's transferred energy, so that's changed it to a different state, a different electronic state. It can't stay stable in that state, so the electron drops down to a closer orbit around the proton, the positive binding center, and releases light in terms of the strong, very high energy light in the extreme ultraviolet that Dr. Ying is going to show you. So you might say, well, what is the acceptor? What's that? Do you want to fire? Oh, okay. So Dr. Ying has the spectrum. Okay, that sounds good. So Dr. Ying has the spectrum already. Looks like he's got a really nice spectrum there. Went very, very well. So he's going to now set up to do another experiment to prove that that light is what you call extreme ultraviolet soft X-ray light. Now the thing about the word X-ray, it's not really X-ray in the sense it's penetrating. Again, this is light that will not even go through 1 centimeter of air. It's a different wavelength region than nuclear, which is bad because nuclear radiation will kill you. This is just very, very mild, can't even go through air type of light, but it's 100 times more energy than light in this room, which your eyes are sensitive to. So he puts this filter in, it will block that form of light, allow visible light to pass. We have 2 other filters in there that block all visible light. So with those filters in, if that signature that you'll see without the EUV blocking filter, if that light goes away, that proves it's this high energy light. It's another confirmation of the source of that light is very, very high energy light. Yeah, Johnny's going to put that up there, and he's going to run another one with this filter that blocks that high energy light. So what you can see is, you can see on the end here, there's a very, very high peak. What that does is integrate all this high energy light over all frequencies and shows it in one peak. In addition, you can see starting around 17 on this scale, 17 nanometers, that is very high energy. When you ionize hydrogen, the energy or wavelength released from that is much, much weaker. That shows up at 91.2. That's the energy just to tear the electron away from ordinary hydrogen atom. So this is extremely, extremely high energy, even compared to that. Typical chemical reactions are even very, very small fraction of the energy it takes to tear the electron completely away from the atom. So you can see that there's peaks here, starting around 17, and then there's a really, really big peak at what they call the zero order, which integrates all this high energy light. So he's going to come back and show you with another experiment that blocks that high energy light and proves, in fact, it is this very, very high energy light is the nature of the emission. So then you might want to ask, what exactly are the kinds of acceptors that make this reaction work? Well, again, there's a remarkable thing about water. The solution to water in terms of this classical theory is that you can have water accept energy in an exact packet of 3 times 27.2 electron volts. That number is a very special number. That is the energy that the electron has relative to the proton in the uncatalyzed hydrogen state. So if you take a negative electron, positive proton, the energy between those two is 27.2. If you have something that accepts an integer amount of that energy, it can cause the hydrogen atom to go down to the lower state. Water has an increment of 3 times that packet of energy. Not water like this. This is water that's hydrogen bonded. That means all the water molecules are interacting. Otherwise, it'd be a pure gaseous state. And even in a gaseous state like in steam, water has molecules that are bound together. What we're talking about is making an isolated water molecule that has no interactions with anything. It's a purely isolated molecule. That's like saying an atom of iron. Like you take an atom of iron, it's very different than, say, metallic iron. So in this case, we can make it by passing this very, very high current through it. It will break some of the bonds in the water, and once that reaction occurs even on a very, very minuscule scale, it self-propagates and then ultimately detonates. We have H atoms, and what we call nascent HOH will cause this reaction to occur. So everything that we need to make this reaction occur is in that hydrated solid fuel material. The solid fuel material that has absorbed some water molecules. So this is a spectrum we've gotten before, published in European Journal Physics D. Editors wrote a note about how major this was. Then we got criticized that it could be due to some high fields. This is a discharge. It's triggered by electron beam. It's high voltage. We did a lot of tests to show it couldn't be due to the high field, but our critics wouldn't accept that. So now we have something that has no high field at all, and this absolutely proves our point that the radiation is coming from forming this new state of hydrogen. It's a very, very important development. So we show the energy, power, and the detonation, and we also show the characteristic signature of this new form of hydrogen that has no alternative explanation as the source of that energy. So would you expect to see this in nature? Of course you would. And what we see is, or astrophysicists see, is evidence that there's an enormous amount of gravity with no visible matter present. You can see a dark ring here. That is identified by astronomers as a ring of dark matter. How do you know that there's matter there? Because you can see galaxies like these that are comprised of hydrogen. In fact, everything you can see is hydrogen for the most part. But here, it's not really emitting relative to this background. And these galaxies have a very unusual structure for galaxies, and the reason why they have that appearance is because they're being gravitationally lensed from some other region in the universe. And you can tell that by changing the angle of the telescope. So this is absolutely seeing is believing, like we're showing visually that you can detonate water. This is showing visually what dark matter looks like. It's a real thing. It's something, it's not something people thought about in terms of theoretical. It's actually a physical phenomenon that you can observe, that there's mass that has gravity, but you can't see it visually. And the reason is, once you form this new state of hydrogen, it cannot absorb or emit light. It's a different kind of reaction. Remember, we have a catalyst that accepts the energy, and then the electron drops this lower state and releases continued radiation. So it's different than a typical mechanism that electrons absorb in typical materials. So this hydrino is unique in that characteristic that it's dark. But we can see it by other analytical techniques. We can show that it rotates, vibrates, has an NMR, and other types of characteristics. So we have a number of analytical techniques that will show this new form of hydrogen. This is just kind of a listing of those. These are common spectroscopic techniques that are used on other ordinary compositions of matter. And there are specific energies or frequencies that absolutely are characteristic of and identify this new form of matter. So I'll go into the system now. What we have is a solid fuel, as you've seen, like the fused crystal. That would be something like silver, magnesium chloride that's been hydrated, forms a pentahydrate. Again, looking at the volume, we're getting billions of watts per liter. That power can be converted into electricity because it's in the form of plasma. So I'm going to show you what the plasma looks like when you film it at 6,500 frames per second. This is a camera that they use to film explosives. So the time scale is much, much shorter than your eye can appreciate. So what this is showing is that the solid fuel is becoming completely vaporized and becoming completely ionized. It's expanding at supersonic velocities, meaning that it is going faster than sound speed. That extraordinary high kinetic energy and highly ionized state is a flow of current. And that flow of current can go into a direct plasma to electric converter. So there's two types of plasma to electric converters that are common. One's called Magnetohydrodynamic, and another one's called plasmodynamic, and we actually invented here at Blacklight. The Magnetohydrodynamic relies on separation of charges in a magnetic field and captured in two electrodes. The plasmodynamic is a similar type of process. And I'll come back and show you more details of the magnetohydrodynamic. So to make that ignited fuel into a continuous process, we have to feed the pellets mechanically in almost a continuous stream. So in other words, you have so much energy, and in energy times frequency, you got power. So if you took one of these pellets and put in 1 a second, then you would have a kilowatt. If you put it in at 1,000 times a frequency of 1,000 hertz, I'll explain exactly mechanically how you do that. That comes out to be 10 megawatts for the amount of fuel that we are proposing to load into this. I'll give you the dimensions of the fuel and the particular characteristics of the machine that we intend to build to deliver 10 megawatts of electricity. So, this is a mechanical carousel that would robotically load fuel pellets. This is not our ideal design. It's just conceptually to give you the idea that you would add fuel in increments, and if you add that increment fast enough, eventually it would appear to be continuous. Like movies, once you go beyond 33 frames per second, your eye sees it as continuous motion, even though that film is discrete individual frames. Same principle. And like an engine, if you hear an engine firing very, very slowly, it's the same kind of idea. When it starts to get very high RPMs, it almost sounds continuous. So, this is our basic system. It's 9 inches by 9 inches by 9 inches. It'd be a 10 million watt electric generator. It has different parts. These are all off-the-shelf technology that can be integrated as parts into this generator. No new technology. So it has a container that holds the fuel. As you see here, the electrodes, it has electrodes, and then they have on it a stationary hub. They heat sink these gears. These gears are driven by a drive gear and a drive gear motor. So the basic idea is you would have fuel flow down from this chamber that holds the fuel, gravity feed, go into these gears. So what happens is the gears would lock, and you can see there's a little triangle, and my finger's here in the middle. So the fuel would be compressed by the gear to make the equivalent of what you saw with the Q Christie, but it would be made by the power being compressed by the gear. Then the current would flow from the tip of the gear to the bottom land, or bottom part of the gear, and then you would get the ignition. So how big would the gear tube have to be, and how many feet, and how fast to make 10 million watts? Turns out to be at a 62 gear, going at 1,000 RPMs, and the depth of the fuel was 2 millimeters, and the base was 4, and the gear was half an inch, about a centimeter wide. That would give you 10 million watts. So it's not very much. To give you an idea, 1,000 RPMs is really trivial. The Formula One racers are limited at 18,000 RPMs for a 4-stroke engine, which is very, very complicated with valves, camshaft, crankshaft, 4-stroke, 4 different parts of the cycle. They're running at 18,000 RPMs. We're talking 1,000 RPMs just for turning gears. It's really, really mechanically trivial. So then we have a chute in the back here to collect the fuel. After the fuel fires, the plasma flows into this magnetohydrodynamic converter, which I'll explain. And then that fuel flows back to chute. It's recollected, goes back into a circulating system like Alder, like they have in the pharmaceutical industry. Goes into another reservoir. You can see there's steam in here. Steam is formed by water falling on a hot heat exchanger. The heat is coming from this heat sunk here, and it's being returned by this cold coolant line. So the water forms steam, the fired fuel comes in, gets rehydrated, and then goes back into the fuel reservoir, and then gravity feeds into the gears again. It's very, very simple. These are magnets. I'll talk about the magnetohydrodynamic system in a second. There's a vacuum pump that pumps down this vacuum chamber. You can see the outline here in white of the vacuum chambers. It's all sealed up, runs under a vacuum. These are magnets for the magnetohydrodynamic converter. This top plate, and then there's a symmetrical bottom plate on the bottom. That is the electrodes that collect the current from the magnetohydrodynamic converter. We would use superconducting magnets. This is a power conditioner. This is a source of electricity for the electrodes. This is a power connector from the electrodes of magnetohydrodynamic back to the power conditioner. Magnetohydrodynamic puts out DC electricity. High current DC electricity. That's what we use on detonation or ignition of these belts. High current DC. So a portion of the electrical output could run the system. So it can be completely autonomous of the grid and also autonomous of fuels infrastructure. And as I show, it can be used for every conceivable application within the size range that you can make these units.
Randy, a quick question. How would you start that unit off-site? What kind of
a battery starter.
Big DC.
Or super capacitor. And then power conditioner would have that as part of the system. So, Sam brought up a point. This power supply is nothing more than capacitors. Like what they are is basically like a can of soda. They weigh about the same. And and you can store a lot of charge in it, and then it can act as a battery for very, very fast delivery of power, a very, very high current. So that's what we would use. Something that's very, very cheap. So I'll explain the MHD here in a second, but basically the cost per unit would be these magnets. These superconducting magnets, even if you want something, they're very, very small. The whole volume here, again, is 9 by 9 by 9 inches. Even if you want some crazy number, like $10,000 a magnet, you got 40,000. You got a couple $1,000 in terms of sheet metal to make the vessel, to make the MHD plasma expansion chamber. You got a couple $10 in electrodes. You got power connectors, power conditioner. Maybe you got a couple thousand there. Source electric power. $10,000 worth of parts set, plus the magnets. So you're well under $100,000. So if you say I've got 10 million watts, that 10 million watts is 10,000 kilowatts. So $10 a kilowatt, that translates into $100,000. So that means this will be under $10 a kilowatt. To give you an idea, solar is thousands of dollars per kilowatt. So you can buy this for $10 a kilowatt, you don't need the sun, and it's like 1 billion times higher power density. And it runs 24/7. So it just blows it away. Same with coal, gas, oil. Their fire is 10 million times smaller power density. It's going to cost at least 100 times more. And you have to buy fuel, and you're tethered to the grid, and you're tethered to fuel's infrastructure. That's what makes this very, very unique. Extraordinarily low cost, no fuel, completely autonomous. So this is on our web page, we have the PowerPoint that actually has these slides and then the different parts. So we're looking for companies to partner up with Blacklight. We're already talking to a number of them now. We want to partner up to make parts. They can make the electrodes, they can make gears, they can make the magnets, they can make the power controller, or they can source electricity for the electrodes, etc. So we will then work with different companies and assemble those components and make our generators. Our plan is our business model is to license original equipment manufacturers to make the units for Blacklight, and Blacklight would lease them to power users under power purchase agreements. So the way Magnetohydrodynamic works is very simple. You have an expanding plasma, which you saw in that video. This collar is a magnetic field that guides the plasma so it goes axially. It goes into a cross magnetic field so the plasma goes along its axis, and the positive ions are bent up and negative ions or electrons are bent down because of the force of a cross velocity in a magnetic field. So there's something called a Lorentz force. So you have a cross field with a flow of charged particles. It's deflected in a mutually perpendicular direction to both of those. So it goes to the top or bottom electrode depending on the charge. That gives you a voltage. Then you can pull power directly off that core. So what magnetohydrodynamic converter is, it's a motionless generator. It's like a generator in a conventional power plant, but it has no moving parts. The current, or the moving part, the part that substitutes for the moving part, is the flow of plasma. In a conventional generator, you have to mechanically spin a wire. In this, the plasma is flowing. That's the conductor, like a wire, that's moving in that magnetic field and producing the electricity. So this is really cheap. The power in the plasma is very high, so you can make this very, very compact. You can make a very, very efficient generator. And again, it's very low cost on a per watt basis.
This one that is an old one that's been around for a long time.
Yes, I'm going to show that. Magnetohydrodynamic is a known technology for many decades. Just go to a volume-filled schematic of that. It's showing, here you can see the placement of the magnets transfers to the plasma flow, and then transfers to both, you have the electrodes. You also have a heat exchanger on the back that would hold this device, because you're going to have some heat produced. We have heat transfer experts working on that. One of the advantages is we have very, very concentrated thermal energy, which makes it much more convenient to remove. So this is just an animation that goes through the workings of this schematic design of our engineered system and shows the different parts and how it works. So I said before, we have different components. There's off-the-shelf parts. One part contains the fuel, and the fuel drops down in these gears. You can see them spinning. You get the plasma forming, flying to the Magnetohydrodynamic converter, makes electricity. The fuel returns, gets rehydrated, goes back into the fuel chamber for another cycle. We've taken the fuel and hit ignition and analyzed it. The fuel is unchanged. It actually works better when you hydrate it, when you reuse the fuel, because that explosion and plasma expansion creates an extraordinarily fine powder with higher surface area than the starting material. But the material is unchanged. Only the water is consumed in that reaction. And we've shown that you can rehydrate it and use the fuel, and it'll actually work better in the recycling of the fuel.
Brandon, can you explain to us how the spent fuel, once it falls through the gears, how is it driven back to the steam unit? Like how is it pulled along?
Yeah, probably just to keep this moving on, I'll take questions in the end, but just to answer that, the pharmaceutical industry has been able to do that for many decades. Typically, to move the fine powders in pharmaceutical ingredients, they use augers. You can also electrostatically charge a belt, and you can use a belt conveyor with electrostatic charge. The photocopier and things like that use the electrostatic, electrosprayers, pollution control equipment in terms of electrostatic precipitators can collect charges or charged particles, fine particles, and adhere them to surfaces very easily to either move them or otherwise manipulate them. But again, these would be manufacturers that we would work with that make pharmaceutical parts, or make parts for photocopiers, or electrospray, other types of conventional parts that we could take advantage of in terms of electrostatically charging and discharging and moving, manipulating fine materials like powders in the pharmaceutical industry.
Yeah. Your business plan has OEM make it the part and electrolyte putting it together?
We probably won't get into assembling. We'll probably have parts made and assembled by a contract manufacturer. Assembled. We want to use as much of the existing manufacturing infrastructure as possible. We try to get products quickly and take advantage of the industry expertise that's already existing. So one thing that I just mentioned, all power sources have a limiting power density. Everybody would like to have their fuel cell make more power, so you can have fuel cells in cars, or they would like to have their car go faster, or their jet go faster with a smaller engine. But there's always limitations in any engineering endeavor. In the fuel cells, they have a limitation of about 1,000 watts per liter because there's a rate-limiting oxygen reduction at the positive electrode. In thermal rankine is a technical term for the type of system that's used in a coal-fired plant. So you have in a coal-fired plant a boiler, that's where you make steam, and the steam goes into a turbine. That's something that takes the pressure build up in the steam and harnesses that pressure in terms of a spinning shaft, in terms of generator. Again, like the MHD, it makes electricity from the conductor moving in a magnetic field, but as I said before, we really don't have that spinning wire, we just have the flow of plasma. So we have a motionless generator, but conventional technology uses a spinning coil. Well, you have to spin that coil. And the limiting power in that, I'll have the questions at the end.
Actually, quick question, slide available.
Oh, yes, these slides are available on our webpage at www.blacklightpower.com. So the coal-fired plant has a limitation of how much power density you can generate because you have to, of course, move the coal in. And then you have to burn it. And you have to get rid of the exhaust. And that takes time. And you have to get the air in there to burn with it. And gas is going in and gas is going out. And all that has to be limited by the rates of those exchanges. And then it's big because the power density is small. To make it practical, you've got to use very huge thermal mechanical systems like big steam turbines. So you can get gradients and you can have the wall melting and damage and things like that. So it's limited to about 1,000 watts per liter. Then there's the thing like the jet engine and the gas turbine to make electricity. And that, you have to bring in the gas and you have to bring in the air and you have to combust them and get rid of the exhaust. And the air heats up very fast. Not like water. You can put a lot of heat into water and it won't go up very quickly in temperature. But gas, like air, goes up very quickly. They say that has a small heat capacity, small ability to absorb heat before the temperature rises. So if the air gets too hot, then it will melt the turbine blades. And those are very expensive. They're like $100 million. You don't want to melt the turbine blades. So you can only run this at a certain rate, and that's about 5,000 watts per liter. Nuclear, you don't want to run it to the point where it goes critical. That is a bad thing, because it will melt down or something disastrous can happen. So there's a certain window of stability that you can operate those plants, and the boiler power density is about 1 kilowatt per liter. It's pretty low. Fusion I didn't put up here, it's actually much worse. It's at least 10 times lower power density, and it's a very lethal radioactive undertaking, and it's very expensive. So it's very, I don't even know if it'll ever make it, so I don't want to put that up there. But internal combustion engine is something in contrast that's very good. Without internal combustion, we would all not be here. We would probably be farming or something like that. Or scrounging for our food. The internal combustion engine is pretty much the workhorse of modern civilization. It makes a remarkable amount of power for its size, and it's extraordinarily cheap. It makes 10,000 watts per liter, and cheap enough that almost every human on the United States can afford at least one. So that's pretty amazing. And everybody has an individual power plant of about 200,000 watts in the form of their car. That is a lot of power. But to put it in perspective, even if you take the most powerful internal combustion engine, our power source is 1,000,000 times more powerful, which means that no one is going to want internal combustion engine anymore, because it is a minusculely poor power source for the future of mankind. So that will radically transform modern society, and it'll be interesting to see the impact it will have years down the road of that kind of power available to individual owners. So one of the things we showed is that spectrum that was the light signature of the new state of hydrogen. In addition, we can show analytical data. So this atom that we formed in this new state can form a molecule. That's the only thing it can react with is itself to make a diatomic molecule like ordinary molecular hydrogen, but this is much more stable, much smaller. It's 16 times more stable than ordinary molecular hydrogen. And the distance between the protons of the molecule, again, a molecule has 2 protons and 2 electrons, and it forms something like a football. It's like a prolate spheroid with the protons at the foci of a ellipsoid. You want to think of it in mathematical terms, but nonetheless, it looks like a football, and it's got 2 centers inside of it, so there are protons that hold the thing together. Very small, but that football can stretch out and shrink. It can, like a slinky, it can vibrate. And that has a characteristic frequency that's 16 times higher than that of ordinary molecular hydrogen. And that dip right there is right identically at that peak, and that's the gas we get off, and it shows that characteristic signature, and there's nothing known in this system that can give any peak there, and that is the smoking gun that we're making hydrinos in this reaction. And there's 12 types of analytical tests that we do that are similar to that to prove we made hydrinos. So it turns out that the Magnetohydrodynamic is a off-the-shelf technology. The Russians are still using it over in Moscow. We're working on getting them to make us a magnetohydrodynamic converter, and they are quite expertise in it. There's groups over in Japan that have large units as well. In the US, we've also run large units, but it's kind of fell out of favor, and pretty much what people use now is gas turbines using fractured gas, we call fracking of gas, and they burn natural gas and use the heated air to turn the turbine. So this is different. This has a combustion chamber. Here's a combustion chamber, and they burn coal in here, and then the coal fire would build up the pressure because, again, they're burning it at atmospheric, just air is going in there. So then it gets heated, and you know what happens whenever you heat something in a confined space, it builds up pressure, wants to expand. So they have it shoot out this nozzle and into this 600 million watt magnetohydrodynamic converter. Now keep in mind, we're going to look at 10 million watts, so it'd be 60 times smaller, but our plasma is 10 million times more energy, or excuse me, more power per volume than coal fire. So that means we can make it a lot smaller because we have so much power in a small space. This is big because you need to flow all that gas through there. And you can't get it to that extraordinarily high pressure. So ours is much more energetic and should be much smaller. So the dimensions I showed you are the best calculations we have presently in terms of the relative scale of all the different parts on that 9 by 9 by 9 meter. So having something that's very small, very autonomous, obviously has advantages and can serve a vast array of power applications. So when you're making billions of watts per liter, it's very, very compact. The fuel is ubiquitous. Anywhere, even in desert, has a vapor pressure of water, and you can get water from humidity and air, water-absorbing materials, or just put water into the system. To give you an idea of how much utility you can get out of water, an automobile that's 267 horsepower, conventional automobile, will go 3,000 miles on a liter of water with this particular system. So it's really incredible how much utility you can get for that as a fuel. On a volumetric basis, the H2O, like this, on a volume per volume basis is 100 times higher. So 1 gallon of water is equivalent to 100 gallons of gasoline in terms of volumetric. And then again, the power density and autonomy are defining characteristics. You could use this to replace the grid and fuels infrastructure and use it for everything. You would use electric heating, you would use it for space and process, air conditioning, you would use it for all the common electrical uses in your home, you would use it for motive power and aerospace and transportation and all forms of transportation in addition to just the motive in your car. So all forms of power can be replaced with this particular type of system. I kind of list the major ones here. So then the question is, what's the nature of that electricity? The different converters we're looking at put out DC electricity. Just as a historical point of interest, you have to ask yourself, why are we not using DC electricity? Because our lighting's DC, all our motors are DC, all our electronics are DC, our heating would be DC, our air conditioning would be DC, everything essentially is DC. Even the cars, the Prius, the Leaf, Volt, they use DC motors. The only one I'm aware of that use AC is Tesla, and it really isn't terribly compelling why they use an AC motor with these. They're different. So the way the power grid works now is you have a central gen station that puts out billions of watts, then puts it out on all these myriad wires that get all smashed when there's a storm like Sandy, and then you freeze in the dark and you're miserable for weeks until they come and fix it. And that's got to be more and more frequent. And that is a very, very miserable state because we have no way of coping without the grid. There's no alternative unless you buy a generator that keeps you up all night or keeps your neighbors up all night, and you have to constantly go get gasoline for it. And when Sandy was here, there was no gasoline, and you had to go completely out of the county to go find gasoline because none of the pumps were working to pump the gasoline anyway. So it was it was an extreme hardship if anybody went through that in test code. The grid is very, very expensive, but the grid is there to transmit electricity. And it was very, very important in its time. The grid uses AC. And the reason AC was selected is not really obvious. Probably no one here knows why it is unless you're a historian. And why it's 60 hertz. Turns out Europe used 50 hertz. And the reason why we're using 60 hertz is because that's when a carbon arc lamp looks like it doesn't flicker to Americans. It didn't look like it flickered at 50 hertz to the Germans. Maybe they're in a beer garden when they're testing. But they said that looks pretty good. So they went with 50, and we said, nah, it's not good enough for America. We're going to go with 60. So we ended up with 60. Now, the idea was to get the voltage higher so you could transmit. But DC is actually better for transmission. You actually have more losses with AC. Then you have to convert the AC to DC in your house, and you lose about 20% of the electricity going down. So there's really no reason to have AC electricity in today's day. We don't use carbon lamps, and there's more efficient ways of transmitting. And we see our technology ultimately becoming DC. So we're contemplating that it may not be a good idea to have a truck and carry a horse around in the back of the truck. It should be good just to go with the truck. So we're looking at a scenario where we would just go with DC power, and the type of power that we would deliver would be high current, and we can control the voltage into local clusters for individual units. A unit of 10 million watts would power 10,000 homes. It would power big commercial installations, industrial installations. 10 million watts will power the Eurostar bullet train. It will also power a super tanker. We could go 50 times smaller. We would probably use plasma dynamic converters, which are smaller, and do individual cars, and maybe even individual homes. But there may be a very, very bright future for DC electricity, given the demand that homes and cars are DC. It's always converted into AC with a DC-AC converter. So this is showing a schematic of how that is done in terms of power flow and then end loads, specific applications. This is another flow chart of those types of applications where we could utilize AC as well as DC power. Then I won't dwell on this, but there are other applications of this new power source. Somebody will probably more than likely try to revive the internal combustion engine and make it higher power density until it melts. Someone will probably try to do central gen with this. And there are designs that are conducive to that. But suffice it to say, we think the optimal design is the system that we showed that would be a DC power source that would be independent of the grid, and we would run electric motive applications. How would so that would you want to pull it up? Oh, is that on the street? Okay, so Dr. He has now put up the calorimetric trace for the calorimeter. You want to go over just what the units are and the numbers? And then, right? Okay, and then Dr. Hu is going to show his spectrum on the extreme ultraviolet. It's called a grazing incidence extreme ultraviolet spectrometer. And this is made by McPherson. It's modeled 310. This is in case anybody wants particulars, they want to try this in their own lab.
Yeah, here we basically measure the input power like surrounding building. So the input power is about 850 joule. And then we use a motor gas limiter. That's a par lag based well-known method to measure the power output. So we got the number here as 1833 is power out. So that we get 980. So it's almost 1 kilojoule that hour.
So you're saying before 1 kilojoule, 1 millisecond, 1 megawatt, 10 to the minus 5 liters is 0.1 terawatts of power. And there it is live, created here at Blacklight. So you've seen it first time, terawatt power densities per liter, controllable, that can be converted to electricity. So now Dr. Liu now is going to go over his spectrum on the proving that the source of that power was in fact the formation of these new states of hydrogen that we call hydrinos. It has a characteristic high energy light, higher than any possible emission of ordinary matter, and cannot be created by a high field or any other alternative explanation. There is no high field present.
The system is shown on the screen. The blast chamber. We have the central volume, so it won't make the pressure too high when it blast the burger. So the UV light needs to be passing the gas to reach the detector. So if the chamber is too small, the pressure is extremely higher, and the light cannot pass the dense gas, so the chamber has to big. And on pass of this chamber, we have two pollution filters. Pollution filter is well known; it can block the visible, and that this is the efficiency curve of the pollution filter. This is the transmission curve. Basically, it allows the photon from 17 nanometer to 80 nanometer to be passed. Okay, the visible will be blocked, and some short wavelengths below 17 will be blocked because of the notch of the efficiency of the combine a spectrum with the blast sample and with two filters on it and without a quartz window. And you can see previously we have a quartz window set up in the system, so the quartz window can block the UV, but let the visible light come through. So we have two spectrum, one with the quartz window on, blue line, nothing. So the quartz window blocks the UV that visible passes, but the aluminum filter blocks the visible. So the spectrum without the quartz window is EUV light. And you can see UH0 or just the reflecting beam, and they are the EUV light. And also you see the features of the spectrum. And they are probably due to the use sample ion emission. There are maybe 2+ ion or 3+ ion, a high ionized pattern. And as the edge at about 17 nanometer, that's equivalent to 70 eV. And our spot welder only supply 50 volts. So with 50 volts, we have a 70 eV photon. There must be some unknown reason.
Okay, that's good. So there's EUV light being emitted and power being generated, and we have a new source of power, systems to harness that power, and we have also we've had 4 validation teams in so far, confirmed the extreme ultraviolet light, confirmed the plasma characteristics of those plasmas, extraordinary energetics that we're seeing, more so than known conventional high explosives. Again, it's not a high explosive. This is only ignited when you throw current through it. It's limited to the very exact position where the current flows. It won't self-propagate like explosives, so it's got beautiful characteristics as a fuel, and it's got extraordinary characteristics in terms of being a source of plasma for direct electrical conversion. Systems appear to be extremely inexpensive, and they use commodity chemicals. And as I said before, here in this last point, the capital cost is projected to be extremely small, about 1% that of conventional capital equipment, no fuel costs, completely autonomous. So we're going to have one of the validators, Dr. Ramon Kachari, who's a very esteemed professor at Rowan University. He's raised $15 million to his projects that test how important his research is. It's absolutely relevant to our work, and that he works with similar types of metals and metal oxides and the like. That's what our constituents are, solid fuel are. He is a PhD from the Indian Institute of Technology, and he is here luckily for us to say a few words, and then I'll come back and I'll take questions.
Thank you, Andy. I'll just introduce myself. My name is Chari. I'm a professor at Rowan University for about 20 years. My area of expertise is inorganic materials, which is what Andy has been using to get rid of these exciting.
Can you get a mic?
Hey, Randy, can you give him a mic?
I don't have a loud voice. Give it here. Can you hear me now?
Yes.
Is this better?
Yeah.
All right. So when Randy informed me about the new findings, I was very curious because I'm also familiar with these chemicals like silver, magnesium, bromide, water, and I also worked with BLP in the past, validating their technology in terms of thermal conversions and electrochemical conversions. So I have a lot of confidence because we were able to repeat what was done here in my lab, independent of what was going on here. And in fact, you can find our report on the website. Those of you who are interested, you can see. So in this particular technology, what fascinated me is the fact that you're using earth-abundant materials, very cheap, safe, clean, and green. That's what exactly the government is looking for, and I was very fascinated because that's the kind of technology that I learned about in Magnetohydrodynamic. We try to work on earth-abundant materials. So we have validated these measurements. I was here, I was working with Julian, Johnny, and again several times. I had been drilling them, okay, let's do an experiment without the water. 1 time, 2 times, 3 times, make sure that nothing else happens, and then control the amount of water. And I must say I'm very fascinated over that mechanism. Now this is going to be a real game changer. And if you have any questions about these chemicals, I'll be glad to answer. Yes, sir.
Stop me, please.
Can I give a card?
Oh, sure.
Next, please. Yes, sir.
From your perspective, given that you work with this and trying to control it, what do you think the biggest challenges are in commercialization for this product?
Well, I work at the scientific aspect of this, like the chemistry aspect of it. The question that I was asking myself is there anything else that could possibly explain the generation of so much power? So, from my own knowledge of the chemistry, especially the organic chemistry, I looked at all possibilities. Like, we work with water for almost 30-40 years. We do the electrolysis of water in my own lab, so we have other projects. And I couldn't find any other reason except the formation of a new state of hydrogen. That is the current theory. I don't have any clue on what else can explain this.
So, but as a scientist, and obviously ready to speak highly of you, you know that there's a lot of other scientists that look at this even more skeptically. Has this latest press release derived a lot of phone calls and interest of trying to ask you questions?
Well,
What do you expect to become later?
As scientists, we all start out as skeptics, right? We begin as skeptics because we don't want to accept anything. In fact, that's how I started with BLP. I was not too confident because this was going against the classroom technology and the knowledge that we have had. But if you look at the report that I gave to BLP, what we did in my library is give exactly what we have done so that people can repeat. I mean, they don't have to believe what I said. I'm telling you, this is what I have done. This is the amount of energy I got. This is the techniques I have used. I did the NMR spectroscopy. I have done the infrared spectroscopy. I have done X-ray diffraction of the materials. And I have reported what I have seen. Now, people can call me anything, but I think I want them to repeat what I have done and tell me if they see anything different. So that's where I leave it. I don't know if I answered your question. Yes?
Just to comment, the amount of skepticism is truly extreme. And Randy pointed out that this is not possible under quantum mechanics. It's worse than that. It's forbidden. This is just flat out forbidden. And that if there is one key reason for the extreme skepticism, that's it. It's worse than impossible. It's forbidden.
Well, my own comment as a scientist. If you look at the theory of superconductivity by the 3 Nobel laureates, they concluded that you cannot have superconductivity above 40 Kelvin. And that was true until 1986. And then came the new generation of superconductors that show superconductivity at 160 Kelvin. Now, Gordy is a very respected physicist. According to the observations that they had at that time, the theory said 40 Kelvin is the limit. But today, we have new material and we need to invent a new theory. So the way we look at it is the theories come and go. We don't know where this will lead for us. I'm not saying this is absolutely perfect.
You're absolutely right, but again, I need hardly tell you the skepticism is extreme, and it's still going to, even with these the smoking gun proof, it's still going to take time to get it accepted.
Absolutely, I agree with you. We need to do more studies and more people have.
No, you don't need to. They need to open their eyes, but it's going to take time.
Power question.
You talk about the new state of hydrogen that you're calling a hydrino. It is the catalyst reassembles and becomes the catalyst. What do you do with the output of the hydrino?
Do you have any specific questions regarding Dr. Ron Contrari's validation? Anybody new?
Yes.
I did have Randy use the phrase smoking gun twice, once in reference to an experiment and once in reference, I think it was to the vibration of the bi-hydrino atom. And you used it once before with reference to a particular experiment. I think it was the extreme brightness of the hydrino signature. Could you go over that just one more time, please?
Well, before that, Dr. Reed, what other studies do you plan to do in the next coming months and quarters? And what other things are you looking for in this? How would you optimize your tests as you go forward?
Well, my job here has been to do the validation. So in other words, come here, inspect all the materials, make sure that everything is done according to scientifically sound procedures. Going forward, clearly there's a lot of things one can possibly do. Perhaps replace the silver with a cheaper metal and try to see if that can be done. And how pure the water should be for the explosion to happen. Can I use any water or
Well, I actually asked a question on this here before, and I'll ask you. That's quite a lot of power. How do you, in the beginning, I wanted you to speak forward, but let's look back for a second. That's quite a lot of power. Were you ever concerned that it might be too much power, given that you were using for your safety?
Well, I think Randy took care of all that aspects. I think this has been worked out so beautifully.
Yeah.
With all the explosions going on, we're all safe here. But I think he was very diligent, in fact, in terms of choosing the right size of volumes.
Yeah.
And I think at this stage, if I'm right, the point of all these experiments is to prove that this power is possible. And my experiments and my validation has confirmed that. And we have done a lot of standard materials. I'll just give you one example. If you look at this graph that we have seen, the calorimetric, the first thing that I asked GDM was, can we also do an indium metal? Because I know exactly how much energy it requires to melt indium metal. And I was there physically weighing the indium metal, putting it in the calorimeter, and making sure that's exactly corresponds to the radiation value. And in the same cell, we ran these measurements, and we saw this increase in the power. So clearly,
So it goes right with the theory.
Are there any rare earth metals used in this process?
not in my validation yet.
Okay, I just wanted to know, so we don't.
Why were you asking this?
So that if it turns out that the only rare metals work, best with this reaction, we don't have to find ourselves going to Bolivia to dig up lithium in order to power our machines here in the United States.
Latest like naphthalene and iridium and all this. I don't know, those of you who are following the market, those prices have gone up in the last 2 years. No, this is the beauty of it. We're talking about permanent materials, cheap materials that we can find in this region, like copper, copper oxide, copper hydroxide, iron bromides. There's nothing rare about these elements that ubiquitous and yes, sir.
Are there any tests that you can conceive of to demonstrate the source of the power being hydrinos or not hydrinos that haven't been done?
Well, in the past validations, that was one of the questions that we were asking ourselves. Is this hydrino or is this something other than these materials? One of the signature tests that we have done in my lab is to look at the nuclear magnetic resonance spectroscopy of these materials. When you have the electron coming closer to the nucleus, you have an upfield shift, and you should see shifts and then more peaks, which we have witnessed in the United States. So that is kind of consistent with what I think has been telling all these years, but maybe a new form of
Is there any other testing?
other tests we have not done. We don't have it on mass spectrometry, but I'm sure we can talk about those things too as we move forward. Thank
I think we can probably wrap it up like next 10 minutes or so. Make some quick questions. Maybe a lot.
What's the, if the prototype is so small and so sourceable, someone needs to be probably willing to help and a pretty good design. What's, if you had the first prototype cost, 1,000 times more than a production model cost, when's the lead time to us seeing the first one and really put all steps to the side? I mean, obviously, if that thing works, you run, what's your model, show us your work. Everything, the world's going to be different. So when do you think it happen?
I would say we're really pushing everybody to do it quick as you imagine. And we see this as something that's more than urgent. So, I haven't got the numbers back yet, but we're talking to different companies about making gears, augers, power supply, power controllers. There's some intermediate-sized companies, around 200 million a year in sales. One company we're looking at, in particular in the Boston area, that they think they can make they do lightning fast prototyping. So we'll be talking to them probably tomorrow. We have another very, very big, they're either Fortune 100, or certainly Fortune 500. They're coming in here with their management team. They would have been here already last week, but they got shut out because of snow, and now they can't come in because of the Super Bowl, or they would have been here this week. So we're going to meet with them early next week. But we're lining up companies, and we're pushing that we have to have this done very urgently. It's off the shelf, no new technology type of scenario. So I don't have the numbers back, but we are working on lightning fast prototypes.
You haven't put a month or a year on that lightning pattern.
I threw it out there. Look, we haven't put a time on it, really, we haven't. But we are getting, I can say this, you saw the fuel, we're doing one at a time. I told Johnny we go down to Atlantic City, get a card shuffler, maybe we can put, like a couple in per second, and we get up in the kilowatt level. That's just a joke. But anyway, we have the machine coming that can do continuous firing of these pellets. And we already have our prototyping expert here working on the gear design and the loading that up, so we can basically run these through like an engine where you have multiple cycles, you go through multiple cycles very quickly. So we would have it putting out a lot higher continuous time average power. So we're going to have everybody back, and we'll do another demonstration when we have that up and going. Continuous machine, that's good. Because what this is a commercial welder, it's a spot welder. They make ones called seam welder. Seam welder is a continuous source of high current, and we're going to adapt the rollers with the gears, and we'll make some kind of way of feeding in the fuel in a more continuous basis. So you're going to see that type of power on a more continuous power flow, and it's going to be really, really interesting in terms of watching that happen.
If you were just to take your design, which is elegant and picture, and say, let's make one of these. Let's assume it's going to work.
Well, it will work. Power, there's no question that power is going to be generated. Then it's just a converter and then the recycling.
How long would it take you to make one like what you designed? Even if it's not the optimum.
I would say we're a huge. I look at what time it would take us to prototype things and what we can put together from scratch. I think if we're a huge, huge company, we can throw the majority of the parts together in a couple months time frame, maybe less. But we got to go put everything from scratch. So we can find some company that's already up and going with all the engineers and has some relevant technology. We can grab parts and they're available. And they don't have to be custom fabricated. We can take power supplies, power controllers, We can take, of course, pumps, motors, they're readily available. And then we can take magnets and different parts are already out there, then it's going to go pretty quickly. It just depends on what we need to have custom made.
In your view, there's no real intellectual property in going from where you are to that machine.
Oh, I wouldn't say that. I've never said it's not.
I guess what I'm trying to get to, if you were to find that large company and so forth, would you be willing to have them joint venture with you to make that machine?
Oh, absolutely. And again, those systems, they should be able to get parts with known technology.
Dr. Mills, have you isolated this diatomic hydrino and/or made and isolated the water analog of it so that you have an ampule or a vial or a flask that you can say this is it?
Okay, what we have is, you go on our webpage, we have 12 analytical tests that I think show overwhelmingly the new state of hydrogen. We had world-renowned experts look at it in terms of analytical. Even the instrument manufacturers that they've said they've had an aggregate probably over 100 years expertise in things like Raman spectroscopy. We have the rotational energy, the spectral signature for vibrating and rotating, the spectral signature for removing both electrons in terms of how tightly they're bound onto the molecule. We have the, as Dr. Ramanchari said, the NMR shift. There's 12 analytical tests in all. They're on our papers, on our webpage. I also have done this particular paper. We have a number on this extreme ultraviolet spectroscopy. The only thing the critics could come up with, and I think their argument was extraordinarily weak based on the visible spectrum and other diagnostics we've done, that spectrum we'd shown and published prior couldn't have been done due to highly ionized lines. There's highly ionized lines in all these spectrums. Dr. Lewis said that is not because the ionized lines are the source of radiation. They're being ionized by this really extremely high energy continuum light coming from this new state of matter. So now we've proven that because we've removed the field. So it's producing an energy of light far beyond anything that can be produced under the circumstances of being run. So I think we have overwhelming proof of hydrogen. Now if you're asking, do we have a bottle? Every time we run these, we always have nitrogen there, we always have other gases there, we have other materials. So what we do is we trap this material in a blank matrix, a matrix that doesn't have any signatures. It gets absorbed in there, and then it becomes very, very powerful in terms of showing the specific signatures, because the background is zero. So you can take molecular hydrogen gas and you have mixed with a lot of gases. It's going to be really, really huge gas to remove all gases and have pure hydrino gas. But you can absorb hydrino because it has very high tenacity to absorb in certain materials. So we can use those like molybdenum, copper, alloy, it absorbs in there. And there's something called a surface-enhanced Raman scattering that we see very, very powerful hydrino signature in terms of rotational energy because of the nature of absorbing there and the way that the laser excitation interacts with hydrino to give us a very, very powerful signature. There's other types of materials that have that same characteristic. They're really quite ideal that we found for absorbing it and showing spectroscopically. It does not make water. The hydrino does not react with anything other than forming a molecule onto itself. Okay, well, you can make a hydride ion, but then that has the propensity to react with a proton, a molecular hydrogen, or react with pretty much any hydrogen source and form a molecular hydrogen. If you can make the hydride ion and keep it away from reacting with any other source of hydrogen, you can make new inorganic hydride materials as an H-. But in terms of essentially anything imaginable under normal circumstances, you're going to make a molecular form of hydrogen much more stable than ordinary molecular hydrogen.
Do you intend to add the electrode generator component to this demo, either MHD or plasma converter?
Well, we have.
And what's the time frame for that? And then you mentioned core validation.
We're just getting back quotes on time and amount.
Can you give any?
Haven't got any indication.
And then you mentioned core validation reports.
I will say this: we made direct plasma conversion systems in our lab. We invented Plasmodynamic on our webpage. There's a publication, IEEE Transactional Plasma Physics, very, very extraordinary, highly reputable journal in that field, and it took us a couple weeks to make it.
And then you mentioned core validations that are progress and you put prior validation and put up on the website, do you intend to make those public?
We'll be making more validations, we'll be doing more demonstrations. We may do a webcast live demonstration. Webcast, stream it on the web.
What is your top 3 engineering challenges?
I think the gears are probably most. And then the question of power storage, power flow, they're pretty simple. With all the expertise there is in terms of power handling. But we've got people working on the gears. I mean, we did get some emulsion of some of the material off the gears, but there's continuous regenerative technologies that you can continuously regenerate the gears in situ. So we're going to try to propose all of that. And use very, very stable materials.
Good, good. What keeps the method?
Well, the other one is heat sinking, but we've got experts working on that. And there's a number of different surfaces we can pull thermal power off of. It doesn't look like it's a problem.
What keeps the positive metal ions from plating out on those plates and getting too thick eventually?
They cool down as they fly through space. I mean, even here we're capturing them as a power. We're not really seeing.
Capture them kind of naturally. They don't.
They seem to recombine if there's a certain kind of flight. There might be some plating issue, but they're inorganic compounds mixed with metals. They seem to stay powder. They seem to make a nano powder when they hit the surface. They don't really plate out. It's actually kind of, it's not really a vapor deposition technique that we're running. We can run materials that would be very, very unfavorable to vapor deposition.
And one last question: how do you make this leap of the imagination?
It's working through the theory. All of it's been predicted theoretically. If we had to rely on trial and error, we would never make it.
Going back to the spectroscopy for a minute, when you first came out with the initial spectrum several years ago, there was some criticism that the spectrometer is not sensitive within the region that you were recording. Have you resolved those concerns and be comfortable? Because that complaint still gets voiced among some skeptics.
Well, yeah, that complaint is completely erroneous and misfounded. A lot of people, what they do is misrepresent things for their own personal gain. What this is an extreme ultraviolet spectrometer that's perfectly valid over the entire region that we've recorded the spectrum. You witnessed it here. You can identify specific spectral lines. We'll put on our paper the characteristic emission of known ion lines. This is what everybody uses for this region of the spectrum. It's called a grazing incidence UV spectrometer. What they're talking about is a normal incidence UV spectrometer. That's a different instrument. So what they'll do is they'll take our modern data or up-to-date data. We keep progressing, we keep evolving, we keep making advancements, and they'll apply all arguments that are muted by the fact they're using entirely different instruments. And that's usually to craft an argument to protect their program or to misrepresent what we're doing. I don't think it's very professional. They should say, okay, they've got the correct spectrometer, they're showing the correct form of radiation, this is characteristic of, it matches their theoretical predictions. And if they have an alternative explanation for radiation, we'll address it. And so far, every critic that we've ever been that's ever been involved in this dialogue is now, their arguments have been dispatched by this recording that's live today.
How do you see this technology applying to jet engines?
Jet engines would be, this could be very, very important for jet engines in the perspective of using turboprops and turbo fans. The motors very, very much miniaturized, extraordinarily powerful, extremely high RPMs. And again, when you have power density 1,000,000 times higher than conventional turbines, which gas turbines, that's what a jet engine is, this could be a great advancement. And so they'd be electrically driven, and there is technology currently, and there are electric versions of fighter aircraft and like, and commercial aircraft on the drawing board in search of a power source. And we have the power source we think would be over the top in terms of specifications for that application. So I think you're looking at a whole other generation of evolution in terms of military and commercial aircraft.
Randy, this startup capacity that you mentioned, what would be
we have just to give you an example, we're looking at building a power supply uniting this with capacitors. There's a, Maxwell makes a capacitor, it's about the size of one of these 16-ounce Coke cans. It's lighter than a Coke can. It's got 3,000 farads, which is a phenomenal amount of charge. And it's about $50 and got a 10-year lifetime. So it looks like it's a very trivial problem to solve in terms of making capacitor-driven power supply with conventional open-shelf parts. The voltage is probably going to be around 6 volts.
You go back in your press release in May of
May 22nd, 2012.
Yeah. You work on continuously running cells, power densities were low.
Yes.
And you talked about the 1.5 kilowatt, cell for a house or something like that. And now we're at 10 megawatts. Like, what was the breakthrough? Describe what happened the last 18 months. Like, what happened that got us on this course? What was the innovation you came up with for all of it?
Well, Blacklight has an extraordinary depth of experience and information that we've acquired in our files over the years. There's an enormous repertoire of technologies and systems, analytical data, spectroscopy that we've acquired, accumulated, and fundamentally it's an aggregation and building upon different concepts. This uses the same catalyst as the CIHT cell, uses some of the plasma characteristics of our prior work that we've done over the decade, or prior decade of work. So we've done about, say, take a decade of work. We've probably spent about 5 or 6 years of that doing the plasma work. We built on that. We switched to from plasma sources as a source of atomic hydrogen catalyst. We switched to thermal solid fuels type systems. Solid fuels type systems, we work on thermally regenerative cells, thermally regenerative fuel, different cell designs to accomplish that. So there's some issues there about continuously regenerating that, and regenerating that over 365 days. And if you're regenerating fuel every minute, how many times that would entail, and what kind of materials we use, and what the propensity was to continuously regenerate that with fidelity each time. So, and then power density issues. So now I invented a new catalyst, this HOH catalyst around 2011. And then rather than looking at billion-watt power plants, enormous steam turbine and generator type concepts where you have like 10-acre plant trying to go directly to electricity. And that was the incentive that the CIHT catalyst induced hydrino transition cell. So it was a direct electrochemical cell. We worked and improved the surface area power density of that by about a factor of 50, as reported in the ENSA report. And then looking at that, pinched plasmas, like this source of hydrino radiation, we were involved with other concepts, other theoretical issues, looking at the catalyst mechanism, the space charge buildup, the propagation, inhibition due to the accumulation of charge in the material, and then in this way of removing that, adding it to the very high kinetics, and then on testing it, then catastrophic. So now we have catastrophic. Basically, the fuel goes almost instantaneously to hydrino, not instantaneous, but extraordinary high rate, much higher than combustion. To make a new state of hydrogen and release billions of watts per liter. So it's building upon all the prior work and theoretical work included.
Would you say, in summary, you started accumulating some advantages and you working at this point? So you can't say it's one thing. It's a
whole lot of influential factors, data, theoretical input.
Where is the hydrinos go after the disproportionate?
Where are they?
Where do they go?
Well, that's one concept I had, that hydrino atom would go to lower states by reacting upon themselves. You have a requirement for the transition of the electron of any hydrogen atom, even a hydrino atom, could go to a lower state. If you had another such hydrino atom, accept the energy at the energy unit of 27.2, which it could. But it seems like what happens when we form these hydrino atoms and they form H214 molecules. We haven't seen any spectroscopic evidence other than H214, and that's the predicted catalyst for this HOH. It's a pretty good product for the HOH catalyst. So it doesn't look like that is occurring to any measurable extent in our cells. It looks like there's the 1/4, we get the 1/4 molecule, and that's the product.
Where do they exit the G?
We can collect it in the powder. We can collect it on witness plates. So we'll put a moly copper witness plate that is a metal that would absorb the hydrino molecules, and we can do ramen on the surface of it, for example. So we'll have different materials to put in that chamber, and they'll absorb the gas that's released, and then we'll do other analytical tests on it. What we call those things getters. They're things that will absorb hydrino molecular gas. But it looks like it would then into the lab and then all of it in the atmosphere and out into space, because hydrino weighs less than air and it weighs less than helium. You can't keep helium in the atmosphere, so hydrino would go out into space.
Do you contemplate a process that is pure setup or another one to combine individual hydrino atoms and other elements to create a
No comments.
Yeah, novel compounds.
Well, so far what evidence we've seen is the hydrino atom reacts to form a molecule, and it seems like that's kind of the product, period. If you make a hydride ion, it can react with any source of hydrogen from a molecule. So if you want to make hydride compounds, you have to make an isolation of any other form of molecular hydrogen or hydrogen source. If you did that, it would be very, very difficult to make them, because you use hydrogen as a fuel to make the hydrino in the first place. So it does look like, from what we found over all the years of research, it looks like molecular hydrino is the product.
Which is, as a comment, is a good thing for a power-consuming site. I mean, if we had all kinds of byproducts, other potential byproducts, that wouldn't be a good thing. Potentially.
I think there's ways that you can make it, but I think for commercial applications, for all practical purposes, H2 1/4 is the product.
One of the things some of the critics raise is hydrinos exist, how come we haven't seen them before? Is there evidence that hydrinos do exist in nature outside of the way that you create them?
Yeah, so I said the propensity, preponderance of data indicates that the dark matter of the universe, which makes up almost all the mass of the universe, is hydrino. What you can see in space, essentially everything is hydrogen, and what you can see, which makes up about 100 times more, is dark matter. Dark matter is just another form of hydrogen. It just doesn't have the same spectral signatures as ordinary hydrogen. But you saw the signature of hydrino, form of hydrogen, in our lab today. That form of hydrogen is formed in space. You can see the same form of radiation emitted on the surface of white dwarf stars. Same exact continuum pattern radiation. Whereas white dwarf stars have no corona, so you can see right down on the surface, huge gravitational field. That's why it doesn't have a corona. So you're looking right down on the surface, and you can see the same type of emission. You can see the same emission from interstellar media. You can see these continuum bands from the sun that aren't absorbed by the corona. The ones that are absorbed by the corona are the ones that you saw. One of the ones is the one you saw today. That has a cutoff of 10.1 nanometers, and it goes to very high energy, about 122.4 electron volts of energy. That's very high. That is absorbed by the gases around the sun, and then the sun has highly ionized species, like very, very highly ionized ions. But then that would indicate that the sun's temperature of the gas around the sun's temperature would be 2 million degrees. But we have molecules in there as well, and you have atomic hydrogen. Those can't exist at those high temperatures. So that means those ions are what they call non-thermal. That means it's not being heated up to the point that those electrons are being boiled off. It just means it's absorbing something with very high energy light, creating those ions. So you can see things in the corona that are very cold, because the surface of the sun is only around 6,000 degrees. So how can you have the gas around the sun being 2 million degrees and the surface is only 6,000 degrees, and that gas is in contact with space, which has essentially no temperature at all. And it's extremely, extremely effective at absorbing heat. So you would expect the gas around the sun to be very, very cold. And it turns out it's not. It's showing these highly ionized states because it's absorbing this radiation. And when you get a star that doesn't have that gas to absorb radiation, you can see exactly the same radiation. And the spectroscopic or telescopic evidence shows that this quote-unquote dark matter behaves identically like hydrogen. And even astrophysicists are saying they think dark matter is some very different form of hydrogen. And that's not me. That's published in Science. And if you go on our webpage and look at this slide on dark matter, you can actually look up in Science and see people like Walmart and others that are saying this really looks like it has to be some form of hydrogen. And that's what we're saying. Dark matter is a form of hydrogen.
And Randy, didn't at one time when you were doing some early NMR validation work where you're not seeing signatures of hydrino, where at first you weren't expecting to see them, and then understanding it that it's ubiquitous all around us, that hydrino can be, small amounts of hydrino can be formed naturally as well. Skip off, is this possible, or?
Well, there are some materials you can heat up. Like if you take a halide and a hydroxide and heat them up, they will form hydrinos. And you can see it by the outfield NMR shift, for example. That's very easy. Anyone who wants to show a hydrino NMR shift, it shifts the matrix peak when you make this hydrino gas. It changes the characteristics of the hydroxyl so that it's in an environment with this uniform hydrogen that has can have a magnetic property to it that causes the NMR shift or the NMR frequency to shift upfield, as Dr. Montecchio was saying. So that's one of the solid fuel classes that we have. We take hydroxides and halides, we put them in the differential scanning calorimeter, and we see very large energy gain. And there's no theoretical energy for it to explain it. We've done that in multiple, very highly reputable academic labs on their instrumentation in their facilities. We have the instrument right there, it's a commercial instrument. If the criticism is that something's wrong about the thermal measurement, I would say they're absolutely, unequivocally, they are wrong. Their theory is wrong, and they won't admit it, and we can show experimentally in our device, we can show it in many academic labs, industrial labs, and labs that make the equipment is unequivocally power. They have to deal with it. Their theory doesn't predict power, they're absolutely wrong. Experimentally, that's what matters. That's why I try to emphasize. You've seen the thing blow up. Theories would say it wouldn't blow up.
Okay.
You're seeing that we're making thermal energy. Theories, conventional theories would say it's not. That means the theory's wrong. Not that we didn't do the experiment correctly. They're done absolutely correctly in commercial instrumentation. You're witnessing live. It means the theory is wrong, not the data is wrong. They have to deal with the data because everybody's coming back, same data. There's no question. The data is absolutely valid. Question in the back.
There was an article on CNNMoney.com in July 2008. You were close to commercializing at that point. So the cells you had, and you were going to go to utilities and power companies. Whatever happened at that time?
Well, it's like anything in technology. We're kind of in unproven ground because we have actually a much greater burden than typical companies and startup companies. We have a harder burden than the United States government or all the European governments, the Japanese, the Chinese governments, the Russian governments combined. They're trying to make fusion, they're trying to make other energy sources, but they have billions and billions of dollars and thousands of scientists. They're plowing ground that's largely already known. We're plowing ground that's completely unknown, undiscovered, unexplored. So we have to work out the theory, the analytical, all the systems, the power reactions. We don't know what the kinetics of the power reaction can be. We don't know if the fuel can be regenerated. We don't know what the survival rate is or its interaction with this new material, what effect this new type of power source will have on it. So we say, look, we've got this new power source, we've got this university, that university, XYZ university, reputable people, carefully studied, years, sometimes 18 months, more than a year, very carefully, credible, meticulously done studies, and this is what we get. We have a source of energy. If that energy was like coal or gas, here's how long it would take to commercialize it. It's not like coal and gas. We have to work out how to thermally recycle the fuel, how to build a power plant that's unlike a fluidized bed or a conventional power plant. So then we have to go through the engineering, we have to go to the chemistry to see if we can thermally recycle. So we found we were working on thermal recycling the fuels. That was a really tough problem. We thought we could recycle one component of the fuel. We showed that at the time that we made that announcement that we could recycle that one component. That seemed to be the most difficult part. Turns out you have to recycle all the components and then reassemble. That means that you're going to have some inefficiencies in the reaction. Reactions are not always going to go 100% completion. So you take the number of times, say you run that every minute, you take the number of minutes there are in a year, you say you did 0.9, and you're going to take 0.9 to that number of times, it turns out you did 0. That means all the fuel is going to be converted to some unreactive reaction product, unrecoverable reaction product, unless you do some other steps to recover. You can certainly do that. And we certainly have other fuels. Or even then a new catalyst, a new system. We have a new system now in these solid fuels that is as simple as one chemical. We have systems that you can add back water, rehydrated. What we have today, as you've seen, is something metal oxide, like the Jumpin' Johnny and the Q Christie. You can literally just add water back and immediately is ready to go back to action again. So, you know, it was a circuitous route, but it turned out the power density is enormous. We can do direct conversion. So in the long run, we're far, far, far ahead than anywhere we've ever been or even could imagine on any of these concepts if we brought those into fruition. Because this could immediately blow away anything we've ever had in the past. Our power densities were typically those of conventional technology. This is unconventional technology. So even if you're out in the market, we would have probably destroyed ourselves in the market. I can't even imagine anything on the face of this planet can be more powerful than this can be controlled. So I think we've got the ultimate power source and the ultimate form of that power to make it into a ubiquitous, self-autonomous, fuel-autonomous, grid-autonomous source of power.
What do you ultimately see, before we applaud, what do you ultimately see, how do we get to 200 kilowatts?
200 kilowatts?
How do we get to 200 kilowatts, down from 10 megawatts down to 200
just,
kilowatts?
That has control systems in that if you change the current through the electrodes, the gear speed, if you change the amount of fuel that you flow into it, you can have thermal power be released rather than plasma to electric by tilting the angle of the electrodes or not pulling the power off the electrodes. You could change the amount of hydration in the fuel in the rehydration step. There's many, many ways. You can store power in power storage. There's many ways you get instantaneous response, so you don't need the grid to be faster than the grid, so you don't need grid backup. But more than that, you can control the amount of power. If you want to go smaller, you just make gears smaller, you have the RPM smaller, you just miniaturize everything. You probably, rather than using the Magnetohydrodynamic, you would probably go to the plasma dynamic, which are basically what a plasma dynamic is. If you have a magnet and you have a pin along the magnetic field lines, if anybody used the magnet, you know the two magnets pull each other together or it pulls in a piece of iron. There's field lines that go from the magnet to whatever it's attracting, or there are field lines that can push something apart. Here we're looking at attracting two magnets making a field that would magnetize a given volume. Then the ions would go in there and they deflect electrodes and give electricity. You can take a pin, like a conductive material, like a needle or a pin, and put it parallel to those field lines and then one perpendicular field lines. What happens, the electrons are very, very light. So they go into an orbit around the magnetic field lines. And those orbits are very, very tight. And they accumulate around the magnetized electrode, but they don't accumulate around the unmagnetized electrode. The positive ions go there. So you get one electrode that's negative, one electrode that's positive. You can pull power directly out of it. It's really that simple. And we've shown experimentally we can get 50% conversion power efficiency with very, very high power densities with just one set of needles. The more set of needles, the more power and more efficiency you get. It seems like it's a very good technique for smaller applications.
And you conceptually...
And you can use permanently magnetized needles. You don't even have to use a magnet. So you just have like iron, if you run a magnet over it, it becomes magnetic. So you would have magnetized and unmagnetized needles, and you can pull the power right out of the plasma vessel.
No superconducting magnets, just these permanent magnets.
Or magnetized.
And conceptually, a box that's...
That box, that reaction box for 10 megawatts is 2 liters.
Right, okay. And so we've got a device, something like this, for 10 megawatts.
9 by 9 by 9.
9 by 9 by 9. And we'd still be happy with a 9 by 9 by 9.
And 150 of that size would run a car. It's going to be really small.
Yeah.
I mean, eventually people probably have a credit card and they just plug it into their house. You know, you get everything miniaturized. It's going to be a huge power. It's going to get down to heat sink. Like, can you get rid of all the heat?
With the new power density that you achieved recently, did it cause you to go vastly modify the bulk of the theory in your mind?
No, the theory's been absolutely predictive. I've been extending it, but the theory what I did is I did a lot of back-end applications like molecules and gravity, cosmology thing. Came back, did everything, unassailable math, all the details of all the atomic physics in terms of lifetimes and states and things like that. But there's never been a backtrack on any of the core concepts that you can apply physical laws, solve what the current of the electron is, and therefrom solve atomic problems using classical physical laws. It's always been absolutely spot on. It's been the most accurate theory in the history of mankind. Everybody says quantum, and quantum is purely made up in terms of adjustable parameters. It's not really a theory. It's just sort of an algorithmic approach where you adjust parameters. So it can't be wrong, because you just wait till the new data comes out and then you just change the parameters.
I think you touched on this, but you're talking about the shaping the world of DC, which is a fine concept, except that there's a lot of things out there that people have that currently, at least start with AC, even if they convert to DC mode.
Well, actually, everything's DC.
Well, but is there going to be a resistance to your technology because of the fact that my house is not compatible with your technology?
It can be wired, so it could be.
Without a big problem. That's my question. We don't have to change every refrigerator, we just change the clock outside.
That's right. The refrigerator runs DC.
Huh?
Okay, just put an inverter on.
You could make it AC if you wanted to, but I think ultimately...
What you're saying is eventually you won't go to AC. I understand that.
Cars.
But right now, I've got a house that's AC, or at least I think it's AC. I don't know what they're doing.
Well, you probably wouldn't be our first customer. We probably your house is too big. And actually, I should say your house is too big for BDC and it's too small for 10 megawatts. It might be big enough for 10 megawatts. I don't know. But anyhow, depends how big your swimming pool is and all your horsepower and all that. But the bottom line is we'll go to the customer that will have a big power load. So we could go. We were thinking originally we'd go to individual homes. So maybe we make a 15 kilowatt unit and we modularize that. Now we make, say, 10 megawatt and we modularize that. So 10 megawatt would do 10,000 homes. So you can go to 10,000 people, or you can just go to one person. So revenues would be $13 million a year off one unit. So that makes a very efficient operation in terms of getting initial sales. After that, the sky's the limit. People are going to make all kinds of moderate manifestations of this particular power source to be sold today.
Well, I'm really just asking the question whether people will if they accept that this works. And say, yeah, well, that's great, and as soon as we get everything that we have converted to direct DC, it will work. And otherwise,
you can make it AC. You can make it AC. You know, the solar power is DC, but they convert to AC. Fuel cells DC, they convert to AC. Windmills is DC, they convert to AC. AC conversion. I'm just saying it's an extra burden of technology you don't need. The only reason why wind, solar, or whatever, they haven't driven the grid to switch to DC yet because they're just a few percentage of the entire grid, and they require backup power. And the only backup power right now is AC backup power. So they're way out in the middle of nowhere. You know, most wind, whatever's, they have big installation. They got to transmit it. They can't have it right on the site. You can't have like 10 megawatts of solar in your backyard or your basement or something like that. So they have these big fields of solar panels, or they have these huge farms of windmills, and then they have to transmit it. So they have to go DC-AC conversion. So they're doing that now. So the technology to do that is off-the-shelf technology. I'm just saying, we foresee the world becoming DC in the future. There was an Edison Tesla debate. It looks like Edison was right. We should have gone DC. And we only had a very small window that AC may have made sense, but ever since then we've stuck with it, and we probably should have been DC all.
Any issues with transmitting DC over distance?
Now DC is supposed to be better for transmission of high voltage than what I've learned right now.
Okay.
Yeah, we won't have to do a lot of transmission because we're going to be autonomous, deployed on site.
What are things you do in parallel, just, commercialize it and you're going to be a royalty rate collector, basically, from MasterCard or Visa electricity. I think it's very much about payments. What are your compliance systems get paid? We're not there yet, or else you're still, that's not part of your brain, you're still not doing how to do that, or it's pointing you off, the lease agreements and contracts.
Well, it's very, very well established. Power purchase agreements. Solar uses that model, and they get paid. All power plants are pretty much power purchase agreements. A lot of companies will have transmission or will have other power that they buy from other power producers, like independent power producers. They pay per kilowatt hour. So that's a very well established model.
It's a little bit different. This is something that you can put your backpack and walk out of the contract manufacturer, and power 10 megawatts in some part of the world, but there's no compliance. That's
in most of the world will be compliant. So the other regions where there's not, Yeah. But, you know, we'll worry about the major markets right now. Okay, very good. Well, thanks for everybody coming in.